Hi everyone, I'm Yangyang Zhang from Beihang University. Today I'm very glad to share our work about failure recovery for parameter server systems. First, I will introduce the background about parameter server. Then I will review the current solutions and their limitations on failure recovery. Finally, I will report the design of our proposed method FreeLauncher and the experimental results. The parameter server architecture plays an important role in the large-scale machine learning, where the server stores globally shared parameters and provides a key-value interface for workers to access. Modern PS systems leverage large-scale cloud computing infrastructures with high-end hardwares like GPUs and TPUs to train models in minutes. However, during training process, parameters might experience unexpected failures and lost the intermediate training results. For fault-tolerant solutions, mainstream PS systems like TensorFlow adopt checkpoint while some earlier systems adopt key replication. However, both solutions have their limitations. Checkpoint method periodically backups parameters to persistent storage like ADFS. Upon failure, the parameters are rolled back to a previous snapshot and lost current updates. But timely checkpoint will bring in significant overhead, up to 3 times. Key replication replicates parameters to backup servers in memory to make sure key copies for each parameter upon update. It's lossless but may increase network usage and delay the convergence. Both methods were adopted without the consideration of machine learning algorithms patterns. Let's look into the parameter server architecture on the worker side. For each iteration, the worker follows the pull, update, push pattern, where parameters are pulled on workers to compute updates. So parameter copies already exist on workers and can be used to recover lost parameters upon failure. A pretty straightforward idea. But there still remain two problems. The first one is the sparsity problem. Some machine learning algorithms like LDA access parameters sparsely. Some parameters may have insufficient number of copies. If the servers and workers holding the same parameter fail together, then these parameters are lost and cannot be recovered. The second one is the stillness problem. Some parameter systems use relaxed consistency like SSP, eager SSP, also known as SSP push, where some workers may hold still parameters that cannot be used for recovery. To analyze the two problems, we conducted empirical experiments with LDA, a sparse model, on a machine cluster. The left figure shows the distribution of parameter copies among workers. We can see that most parameters have at least 3 copies. The right figure shows the distribution of clock difference under SSP and SSP push consistency model. We can see that most copies are within the stillness bound. It's concluded that only a very small fraction has insufficient copies or is too still. So here comes the FreeLauncher, or proposed efficient failure recovery method. FreeLauncher mostly leverages parameter copies on workers and uses selective replication to deal with the sparsity and stillness problem. FreeLauncher selectively replicates the latest copies of the sparse and still parameters, so as to ensure parameters to have at least k up-to-date copies, whose stillness is within the stillness bound. As analyzed before, only a small fraction of parameters needs to be replicated, thus introduce very small extra overhead. Upon failure, FreeLauncher collects copies of the lost parameters from surviving workers. During the failure-free training process, we keep track of workers that ever pulled the parameters. And at the end of each iteration, parameters whose number of up-to-date copies is less than k will be replicated to other workers to make it have k copies. For failure recovery, the recovery flow consists of 3 stages. The first is the replace stage. After failure, each failed server or worker is replaced by a new replacement server or worker. The second is the recover stage. Each replacement server would collect the most recent parameters from all surviving workers. The third is the resume stage. After all servers and workers are resumed, the application will be fully resumed. For server recovery, first surviving workers check their local parameter clocks and send to the replacement server. Second, after receiving all parameter clocks from surviving workers, the replacement server would select the workers with the most recent clocks for each parameter, then group parameter IDs to the surviving workers. Third, after receiving the parameter IDs, the surviving worker would check its local parameters and send parameters to the replacement servers according to parameter IDs. For worker recovery, we just launch a new worker and join the training. Our experiments were conducted on an A machine cluster. We have implemented FreeLauncher on TensorFlow and Python. We use ResNet, MLR, and LDA for application benchmarks. We choose checkpoint and key replication for baseline method. We are curious about failure-free overhead, recovery time, recovery coverage, and loss for metrics. The result shows that checkpoint introduces up to 3 times the overhead, while key replication introduces over 10% overhead. For FreeLauncher, we found no noticeable overhead because only a very small fraction of parameters need to be replicated. For recovery time, FreeLauncher is faster than checkpoint because FreeLauncher recovers parameters from worker's memory, while checkpoint needs to be load snapshot from disks. But FreeLauncher is slower than key replication because FreeLauncher needs to be additional steps to collect the clocks from workers. For recovery coverage, FreeLauncher is able to recover all lost parameters if failed servers is less than k. And it may also recover lots of parameters, but maybe still if field servers is greater than k. For the case of 4 field servers on LDA, there are 2% parameters is out of the stillness bound. We compared the training loss of recovered parameters and failure-free training loss. It can be observed that FreeLauncher has no obvious errors and training delays to the training loss. Thus, FreeLauncher is lossless. In summary, FreeLauncher is a costless and lossless failure recovery method for parameter server systems. Please refer to our paper for more details. That's all. Thank you for listening.